Hello everyone, welcome back. In the last class, we have seen what is digital signature and formally the definition of digital signature was given. And then what are the attack goals of adversary for the digital signatures? That's what we have seen in the last class. Let us now see some of the digital signature which were uh, in use. Today, digital signature is one of the most useful primitive used for authentication. The first international standard for digital signature was adopted in 1991, and that was RSA signature. Later in 1993, digital signature algorithm was adopted. So, in 1991, RSA signature was adopted, and in 1993, DSA. DSA is actually digital signature algorithm or a digital signature standard, DSS also. And in the recent literature, the elliptic curve variant of DSA is very popular and studied extensively. We'll start with RSA first. So let us see what happens. See, in the case of PKC and in the case of signature, what is the relation or what is the thing? Okay, in the case of PKC, there is Alice and Bob. Okay, and Alice want to send some information to Bob, send some message to Bob. Then what Bob has to do? Bob has to generate public key and secret key, and with this public key, Alice used to encrypt the message with the public key of Bob, and he will send it to him. And with the secret key, he can decrypt it. Correct. So here, sender is this guy, Alice, but the key generation is done by Bob, the one who is going to decrypt it. In the case of signature, there is two things, signer and verifier. So here the signer will generate the keys, that is public key and secret key, and he is only the one who is having message. So this is the message he is having, and he will sign on this message. So he'll put his signature, correct, digital signature, and both the thing will be sent to the verifier, the one who want to verify. Suppose this guy Bob want to verify, so with the help of public key given by signer, he can easily verify whether the b is equal to 1 or 0. If it is 1, then it is valid, otherwise it is false. So this is a small difference between the PKC and signature. In the PKC, the person who is having message, he don't do the key generation, he will use the public key to encrypt. Whereas here the signer, the one who is here, the one who is signer, he will generate the public key and secret key, and he is going to find the signature along the message whatever he is having, he will put the signature on it, or he will find that delta, and then any verifier entity can verify the signature on that message. Okay, now let us see the RSA signature is based on the parameters of RSA crypto system. Like the RSA crypto system, the security of RSA signature is based on difficulty of solving integer factorization problem. Okay, so let us see the scheme. First thing is setup. Say Alice selects two random large primes large primes P and Q and computes that is n, which is P into Q. Okay, and Alice also select a hash function. Select a hash function, say h, whose input is from 0 to 1 star. It is arbitrary length to a fixed length Zn star. So this is the setup. Now what is the key generation? For key generation, it is similar to your RSA crypto system. Alice selects an integer v which belongs to Zn star such that this v is less than phi of n. Okay, and GCD of v comma phi of n should be 1, where phi n is the Euler totient function. She also computes an integer s such that s belongs to Zn star such that SV is equal to 1 modulo phi n. That means what? Why the GCD of V and phi n should be 1? Because V should be invertible. I should able to find S such that S into V is equal to 1 modulo phi n. Finally, the public key for Alice is V and AND, and secret key is S. So this S is actually signature key, you can say. That is signing key. And that is secret. And what is public key? It is verification key. Okay, now since we are done with key generation, let us start with encryption. How do you encrypt? To sign a message M, we are having M belongs to Zn star, as in the case of RSA crypto system. Or actually M should be belongs to Zn star if hash function is not used, but we are using hash function, so no need of this thing. We'll be using hash function. What Alice does, Alice computes. See, Alice is the one who has generated the keys, and he is the one who is encrypting, who is the signing on the message. So he will first compute hash of M. Hash function I had already taken. So he'll compute hash of M. Let me call it as H, and he will compute the signature. Signature sigma is equal to H raised to S modulo N. See, one thing you should ask, why he is calculating signature on the hash function, why not on the message? See, message is of message can be of any length, but hash function is having fixed length, and there are some attacks which we can prevent by taking hash function. We'll be discussing later on. Okay, so what I am doing, first I was having message, I put it in the hash function, I got the image H, and then how do I compute the signature? Signature sigma is equal to H raised to S modulo N. Okay, so Alice sends the signature. Alice sends the signature sigma along with the message M to Bob. Bob is the verifier here. So now let us see what is the role of Bob. How will he verify the signature is from Alice? There is no decryption, I'm sorry, and even it is not a, I'm sorry for this, this is not an encryption scheme. Here it will be signature. And then next is verification. To verify the signature, Bob computes sigma raised to V modulo n, and he will get some say h1, and he will compute the hash value. Also he will compute hash of m. If yeah, hash of m will be h, that is already if this h and h1 is same, then he accept the signature. Okay, so he accept the signature sigma if and only if this h is equal to h1. Correct. So this is how the verification is done. Correctness is as follows, because see, I am putting sigma raised to b. What is sigma h raised to s? So it will be h raised to sv, and sv modulo phi of n is 1. So it will be the hash function. Now yes, I told you that why do we need hash function. The question is why to use hash function in RSA signature. Okay, so simple example is known message attack. See, suppose if the attacker has two message signature pair, say m1 comma sigma 1 and m2 comma sigma 2, then he can create signature on third message. Then he can create signature on third message, say m3, which is m1 into m2. How will he do that? He will just multiply both the signatures, that is sigma m1 and sigma 2. So that let me see, m3 raised to sigma, it is just m1 raised to sigma, m2 raised to sigma, sorry, not sigma, should be s. I'm having the signature m3 raised to s is what, m1 raised to s, m2 raised to s modulo n. And so you already know that delta 1 and delta 2, it is just delta 1 delta 2 modulo n. So you got the signature. So even with properly using, he can get the this was the known message attack. Even chosen message attack is also possible. Suppose the Alice first what he did, suppose the attacker wants to forge a signature, he want to find a signature on this message. So what he will do, he will randomly select m1 and he will get the signature from the Alice on m1. So suppose m1 and I'm having sigma 1, correct, and m1 is such that now he will ask signature on m2. So then what is m2 actually? It is m1 inverse m. So he will ask the signature on m2, so he will get this sigma 2. Then what he will do, he'll just multiply the signature on both the thing. He will multiply sigma 1 into sigma 2. What he will get? He will get a sigma which is signature on this M, if you see, just by with this property above mentioned. Correct? See, because this sigma 1 is m1 raised to s, sigma 2 is m1 inverse m raised to s. Correct? Now if I multiply, I'll just get sigma which is m raised to s. So I got the signature on my message as I wanted. Okay, so this was all about RSA signature. Now let us see the next one, that is ElGamal signature. The ElGamal signature scheme is based on the parameters of ElGamal crypto system, like the ElGamal crypto system security of ElGamal crypto system was based on a discrete logarithm problem, correct, over the finite field. So let us see the algorithm. First I'll set up. Alice randomly selects a sufficiently large prime P and a primitive root G and a primitive root G modulo P, okay, of set P star. Alice also select a hash function select a hash function h from 0 1 star to 1 2 up to p minus 1 or zp minus 1 zp star. Okay, so this is what the setup is. Now let us see key generation. Alice further selects a random value A which belongs to 2 to p minus 2 and computes this capital A which is G raised to A modulo P. Okay, so the public key, what is secret key? Small a. Public key which is verification key, which is P, G and this capital A. And what is signing key, which is also secret key, which is small a. Okay, now let us see how the signature can be done. How can we find signature? To sign a message M, suppose M is the message, Alice randomly selects a key belonging to 2 to p minus 2 and co-prime to p minus 1 and co-prime to p minus 1. See, further computes following two things. R is what? G raised to k modulo p, and S which is k inverse multiplied with hm minus AR modulo p minus 1. Okay, so this is R, this is S. Finally, he output the signature. Alice outputs the signature. Delta is what? R comma S. So here the signature is actually of double. It is of double size on message M. Okay. Now for verification, see, suppose you got the message and signature pair. Now it is that you want to verify. Bob first check. Bob first check whether R is less than P minus 1 or not. Okay. So if the above condition is not satisfied, he reject the signature. If the above condition is not satisfied, he rejects the signature. Okay. Otherwise, he check the following. Otherwise, he check the following. We'll check this e raised to r into r raised to s. This is what g. This should be g raised to hm modulo p. If you are getting this, if the above relation holds, he accept the signature. Otherwise, reject. If this holds, he accept. Otherwise, reject. Now let us quickly see the correctness why this is true. Correctness, see what is this e raised to r and r raised to s. E is what? G raised to a, so it will be g raised to ar. And what is the value of r? It is g raised to k. So it is g raised to ks, but now we know the value of s also. So this g raised to ar, keep it as it is. G raised to k, s is what? K inverse hm minus ar. Okay, which is equal to, see, this k inverse getting cancelled. G raised to minus ar will get cancelled. You will get g raised to hm. Correct, modulo p. So this correctness is true actually. The signer must be careful to choose a different key uniformly at random for each signature, and to be certain that key or even partial information about key is not leaked. Because if you somehow or some partial information about key is then an attacker may able to deduce the secret key, small a. And as we have discussed that security of this ElGamal signature is based on security of ElGamal crypto system. If we compare RSA with ElGamal, then you see that first of all signature size for modulus P of size 1024 bit, size of ElGamal signature is 2048 bit, whereas in RSA it is 1024. So this is called message expansion. The size of ElGamal signature is double than RSA. Now let us see one more signature scheme, that is called digital signature algorithm, DSA. The ElGamal signature was proposed in 1985. Later in 1991, this NIST proposed DSA, which can be observed as a variant of ElGamal signature. To use as digital signature standard, they considered it as official FIPS 1993. Let us see the setup. Mostly it is similar to the ElGamal system. So setup part is same. I'll just select this. Oh. So the setup is same, that Alice randomly selects a sufficiently large prime P and then primitive root G and a hash function. Large prime P, primitive G and hash function. Okay. And key generation, again it is same as ElGamal signature. Here one more additional property, additional prime which we will be taking, same as ElGamal. Here an additional prime Q is also chosen, which is a prime factor of P minus 1, which is a prime factor of P minus 1. Okay. Further, to compute private key, the signer chooses A, which is less than Q, and he computes capital A, which is G raised to A modulo P. Okay, so the public key is P, Q, G and A, and secret key is small a. Yeah, as I told you, public key is same as verification key, and secret keys are signing key. Okay, so this is your key generation. Next is signature. How do you sign? To sign a message M, signer generates random signing key K, which is less than Q, and computes. Even instead of saying signing key, it should be actually just random number. Yeah, compute the two things. R is what? G raised to K modulo P, and then take modulo Q also. Okay, and then S is what? It is K inverse HM plus AR. In earlier it was minus AR, here HM plus AR is there modulo Q. Okay, so the signature on message is R, X. sigma which is r comma s. Okay, now let us see verification. So signature. So receiving the signature, suppose you got this sigma r comma s on message m. Okay, verifier first check whether r is less than. Verifier first check whether this r is less than 1 to q minus 1 and s is less than 1 to q minus 1. If yes, then he computes. If it is no, then he rejects the signature. And then computes x is equal to s inverse modulo q. Okay, y is equal to hm into x modulo q, and then z equal to rx modulo q. So he computes this x, y, z, and v is equal to g raised to y multiplied by e raised to z modulo p and at last modulo q. Correct? If this v is equal to r, if this v is equal to r, then the signature is verified. Then signature is verified. Let us quickly check the correctness. Correctness is easy. Yeah, let me talk about this g raised to y and e raised to z. So what is g raised to y? It is g raised to hm multiplied by x. But what is x? It is s inverse. I'll write hm into s inverse multiplied by e. E is what? G raised to ez. So what is z? Rx. But what is x? Again s inverse. Okay, yeah. Actually, I wanted in terms of y, no? Okay, should be r. Now it is just 1 second. It is rx. So whole thing can be written properly. So g raised to I can take c s inverse common. So g raised to s inverse, and I'm having hm plus ar. But we know what is hm plus ar. If you see here, yeah, k inverse hm plus ar is equal to s. So hm plus this hm plus ar can be equal to sk, or even I am having s inverse of this. So multiplied s, I will be having the g raised to k actually. So this will be just g raised to k. But what is g raised to k? Which is r. So hence the correctness is true. We had said that if v is r, then signature is verified. Yes, signature is verified. And again here underlying idea of The security is on DLP problem. Okay. We use SHA-1 as a hash function. It is strictly recommended for existential forgery to avoid the existential forgery. DSA is efficient in verification than ElGamal. This is crucial because verification can be repeated many times for a signature. If you talk about the signature size of DSA is 6 times smaller than ElGamal. Signature size of DSA is 6 times smaller than ElGamal, hence 6 times faster. Six times faster. And if you take elliptic curve DSA, then it will be still reduced. So we'll be seeing that. Okay, so now next let us see the elliptic curve DSA. Digital signature algorithm. We call it as ECDSA. Okay, let us see setup. Setup is same as your ElGamal signature. If you talk about key generation, so Alice chooses the finite field FP, and an elliptic curve. If you don't know about elliptic curve, please check my previous video. I had done everything about elliptic curve. And a point, we call a point G here, which belongs to the elliptic curve FP of large prime order Q. Order Q. Okay. She further selects a secret number. Secret number S lying between 1 to Q minus 1. Okay. And computes V, which is SG, and it will be again in your elliptic curve EFP. Okay, so what is the public value? Public key is what? P, Q, and the elliptic curve on the group G. Okay, and And V, yes, public key is actually verification key is V. And our signing key, or you say secret key, is small s, this small s. Okay, how do you calculate the signature? To sign a message M, Alice selects a random integer. Alice selects a random integer E belonging to 2 to say Q minus 1, computes EG, which belongs to your EFP. Okay, and let me call S1 is equal to EG modulo Q, and S2 is equal to H plus SU E inverse modulo Q, where S1 is U comma V. This one is U comma V. I'm talking about this point. So what is signature? Signature delta on the message digest H. Signature on message digest H is S1 S2. Okay, now for verification, to verify the signature, suppose S1 S2 I am having, and the message H which is as of M, this is what I'm having. Bob computes, first compute V1. Bob computes V1, which is H into S2 inverse modulo Q. V2 as U into S2 inverse modulo Q, and you will calculate this V1G plus V2G. V2V, sorry. Finally verify whether this V1G plus V2V, whether if I take modulo Q, is it equal to S1 or not? Okay, so let me just do the correctness part. So what is this V1G plus V2V? So what is V1? It is H S2 inverse G plus U S2 inverse SG. Correct? So I can take S2 inverse G outside. I'll be having what? H plus SU. So if you see what is H plus SU, so it will be S2 inverse G ES2, which is equal to EG. And what is EG? It is S1. So as expected. As this ECDLP appears to be harder than DLP, so the smaller parameters serve equal security as achieved by DLP. Correct? So this ECDSA is the elliptic curve analog to DSA. Whatever DSA we have seen, we have just write everything in terms of the by the elliptic curve. So now, yeah, as I told you, say for example, if the DSA requires at least 1024 bit key to achieve 80 bit security, this ECDSA require only 160 bit key. So that is so efficient. So the ECDSA can be up to 15 times faster than RSA. Let me just write this. For example, where the DSA requires 1024 bit key to achieve 80 bit security. The ECDA require only 160 bit key and with the same security level. So that means ECDSA can be up to ECDSA can be up to 15 times faster than RSA, depending on the platform of implementation. Platform of implementation. So another importance of ECDSA is that its security relies on the solution of ECDLP, and the unavailability of efficient algorithm for the solution of ECDLP makes ECDSA a good choice for a robust signature algorithm. Okay, that's all. Thank you so much.